Greetings and welcome to Week 3, Unit 4 on Sample Curriculum. In the last unit, we understood the nature of skill enhancement courses. Now, we'll try to put all the elements of the curriculum together and work out a sample. And I'm mainly presenting the sample curriculum of ECE program because of my more familiarity with that. And for other branches, similar attempts can be made. Now we start with as we said, any program should meet the 11 program outcomes of NBA and 2 or 3 program specific outcomes as decided by the department. Okay. Now here we wrote 2 program specific outcomes. One can write 3 also. One can change the wording of this. Let me read. Specify, design, prototype, and test electronic systems that perform analog and digital signal processing functions as per user requirements using electronic components currently used by the industries. Please note the emphasis on presently used electronic components by industries. Then next one is architect, partition, and select appropriate technologies to implement a specified wired and wireless communication system. These are the 2 PSOs, and you can provide specialization through 3 bouquets of electives. One can alter this, one can make even 4, or one can make a long list of electives from which you give the freedom to the student to select anything he wants, and so on. 3 bouquets of electives suggested are for ECE UG program are electronics, communication, and signal processing. These are the 3 bouquets that we will present. From this, the department has a choice to select. Now, we have made some assumptions in designing a curriculum for ECE. First thing is, any curriculum that is proposed for a program is not the only solution. There is nothing like a unique curriculum. It is all a decision made by the faculty together. The only thing is, all the faculty need to be sensitive to the current market requirements and what kind of skills and knowledge set the graduate student should have. And for this, the department should have some process in place where they will be continuously monitoring what is required by the industry. Curriculum of the program is to be designed to meet the POs of the NBA, PSOs identified by the department, and the goals of NEP 2020, which are multidisciplinary, holistic, and multiple entry, multiple exit. These are the requirements of NEP 2020. So as we mentioned, keep track of the state of the subjects and current industry practices. And curriculum should not be dictated by the available textbooks only. It can be very much dated. Some books are popular still in spite of the content being completely outdated by decades. Somehow in India, some textbooks are still, you can say, legacy books which people continue to use. Courses should not be overloaded to ensure sufficient engagement of the students with the new knowledge and practices. See, if you want the students to learn well and give enough time to the students to practice, then the curriculum courses should not be overloaded. Because of the current state of the subject, you should not be going overboard to keep on increasing the content of the course. If you increase the content of the course, then it is difficult for students to get engaged with the knowledge because you have too much to do. Then all learning starts becoming superficial. When it becomes superficial, somehow it percolates to the examinations as well. Even the assessment starts becoming superficial. And another one, an assumption that was made long time back and which has drifted for so long, there should be one course of for each branch, for the 4 branches, basics of 4 branches of engineering to be offered. That has become the practice for a long time, though recently some of the institutes are giving that up. But we are proposing don't go into that dimension at all. Multidisciplinarity can be addressed in a different way, that we'll see. But directly, some 4 3-credit courses are offered in every branch, where basics of civil engineering, basics of mechanical engineering, electronics, electrical, computer science are all offered. You can avoid that. You can save a considerable number of credits. And another one, as the number of credits is restricted to 160, plus we want content to be not overloaded, courses not to be overloaded. So one of the things that one should do is repetitions of any subject matter should be completely avoided. That is, you teach something in the context of one subject and teach the same mathematics or basic science in the context of another subject and so on. And another one, whenever a student comes into one particular subject, he should understand why he is made to learn that particular subject. He must have a feel for it. If he says it's just because it is compulsory, he cannot be motivated. It should be properly related to, let us say, to the knowledge and skill set that he requires to attain at the time of graduation. So, special effort to be made in each course why they are learning, especially for engineering science and some basic courses. And these days, it is required some AI features are to be added to some courses at least. And also there had been a practice, there can be no credit mandatory courses. The concept of mandatory non-credit courses is utterly stupid in our opinion, because both the teacher and student will be totally unmotivated to go through the subject. Why? That means any work that the student does, he doesn't get any credit at all. If you consider that it is important for the student to know, then make it a part of the curriculum. So we strongly recommend no compulsory, no credit courses to be offered. Okay, these are the assumptions we have made. I hope you agree with these assumptions in designing a curriculum. These are valid for any branch. Now, I need to spend some time with regard to some subjects in ECE that need reconsideration, because some of the things are stuck in for about 2 or 3 decades old way of handling things. Take the subject of analog electronics. You start with the physics of devices, what a diode is, what a transistor is, and even you take something like 8 to 10 lectures on the diode itself, and subsequently on transistor, write a lot of equations how the electrons and holes move across the barriers. And with all that knowledge, you may understand how a transistor works. But please do remember that nobody ever in current day practice builds any circuit with single transistors and single diodes. So it is all a meaningless knowledge that we impart and waste a lot of time in doing that. what are the components that the industry starts working if you want to build anything in the analog dimension? First, the basic components are op-amps, comparators, devices like that. There are only a few devices. Of course, op-amps, if you take, you have a wide range of them. That they need to understand. But op-amp directly is very different from a single transistor. So you don't even have to start with the physics of a transistor or a diode. Diode now mostly can be looked at as a function. That is, it admits current in one direction and it doesn't admit current in the other direction. That's all that you require to know. Whereas in high current areas, yes, you need to understand the physics of it. If you want 20 amperes, 30 amperes, 100 ampere diode, yes, there is something that needs to be understood. But that can come at a later stage. So understanding transistors, modeling the transistor for various frequency ranges, various voltage ranges, is that of persons who design those devices. And those devices are not designed by every electronic engineer. There are a few specialists in big companies, they actually do that and they require that knowledge. So that knowledge is not necessary to be given to the undergraduate students. If they specialize in that area, yes, they can go through that. So with respect to analog, you need to completely base the course on the components that are available currently in the market. Then coming to digital electronics, here people have tried to adapt themselves to the changing things, but still many colleges have laboratories where they put one gate and give two voltages at the input and look at the output. That kind of experiments are utterly meaningless. Like NAND, you start talking about how a NAND gate works, how a OR gate works, how do I design a simple logical expression and realize it by using gates. All that is totally irrelevant today. Because actually most of the manufacturers have stopped making devices at that low level of integration. You don't go to the market and buy a, let's say, even a 4 NAND gate IC, because it occupies the space on the printed circuit board. So you only look at digital functions rather than digital gates. So call it digital electronics or digital systems right in the beginning, but they're required to understand what a NAND function is, what a OR function is, and how do when I put these functions together, how can I produce a certain, let's say, a combinational function or a sequential function. That they need to know. But they don't have to work with very low-end devices in the laboratory or in the class. So right away with these digital functions, one can start designing something with, let's say, using one of the hardware description languages like Verilog. The first course in digital systems can be how do you realize combinational and sequential functions using something like Verilog. Follow or understand all the features of a Verilog before you can use it. You can only present what is relevant in this course, and the other features can be postponed to a later stage. So one course that you can have on digital functions of digital systems. We spend a lot of time in trying to simplify a logical expression using Karnaugh maps and a few other methods, very simple ones. Even that is meaningless because no practical circuit will work with 5 to 6 variables. Beyond 5 to 6 variables, Karnaugh maps, none of them will effectively work. They are not useful at all. So spending a lot of time on learning Karnaugh maps is worthless. All that you require is maybe some kind of algorithm that you can use to simplify a given digital logical expression. And finally, what happens, most of the minimization techniques are based on reducing the gate count. Here, gate count reduction is not the goal when you build a digital circuit. What you require is the footprint. How much space does the digital ICs occupy on the printed circuit board? And the other feature is, if it is a high-speed circuit, then what is the delay time from the input to the output? These are the only two things that you need to attempt. And none of those things can be solved by following these traditional minimization techniques. So please bear that in mind when you design this particular course. Most of the things that we have been teaching, they are useless now in the current context. Then comes the course on control systems. Control systems, you can call it feedback control systems or whatever you want to call it. Feedback control is a very important feature of anything in the world, right from biology to anything. So a knowledge of understanding the behavior of a feedback system and how do you design the required behavior is part of the control systems subject. But what happened is, if you look at the textbooks right until recently, most of the things were based on frequency domain techniques because of the historical reasons. Because most of the initial concepts of control systems came from the communication subjects. So in communication, you worry more about frequency domain behavior, but frequency domain behavior doesn't make that much sense when you look at, let us say, a mechanical system or a process control system or something like that, where control is applied. Okay, so, but we didn't have choice because we don't have a simple method of finding the roots of let us say third order or fourth order system. So people had to depend on frequency domain techniques to find out how far they are from the j omega axis, how system behaves when it is very close to j omega axis, and so on. But then again, and most of the material is restricted to single input, single output systems. If you want to go for multi-input, multi-output systems, though there are some frequency domain techniques, but they're very limited, and the best thing is to go to time domain. So why start with frequency domain and then make effort to switch over to time domain? Right from the beginning, now you can go into time domain methods of designing or understanding feedback control systems. Another, historically, what happened is, when you are unable to find the roots of a third order, fourth order system, you had to resort to these frequency domain methods where the roots are located. When the roots are at certain points, how do you determine the behavior of the system? And then you talk about Bode plots and so on. All that was relevant, was used for several decades until what you call software systems like MATLAB came into the scene. Now, by just a click, you can find the roots of any order polynomial. So why do you require so much effort to determine the roots of a polynomial through all those long-winded methods? So right from the beginning, while you can sensitize the students to frequency domain behavior a little bit, but most of the control systems activity should be predominantly remain in time domain methods. And on top of that, now you have MATLAB can give you such an interesting what do you call, user interface, that you can very clearly see the behavior of a control system very nicely in a graphic form. So the presence of a corresponding software, if you find MATLAB expensive, you can use Scilab. There are lots of courses other material available in training in using Scilab. And another one is the control systems can be taught in such a way some of the concepts can be transferred to the subject of analog electronics. Once you use op-amp, it is required that you have to spend time in how do you manage the feedback behavior of analog circuits there. Because what is analog circuits? You have op-amp, that is a very large gain that you have, and then by using feedback, you are trying to make that whatever function that you want to realize. And the feedback concepts are very relevant to analog electronics as well. Then comes another major subject, which my survey shows that neither faculty nor the students like the subject, that is electromagnetics. That is because most of the textbooks, they present it more like a physics subject, and also the related mathematics is fairly difficult to follow, and a lot of mathematical background needs to be acquired before you understand that. So you must have a certain goal towards which you want to treat the electromagnetics. Do you want to go towards the antenna and that kind of thing, microwaves and all that, or you want to go towards electronic packaging? We'll presently see. So when you design the electromagnetics course, you must have your target clearly in mind and work towards that. Design either the laboratory or the subject matter itself, syllabus of the course itself. If you have, I try to talk to several electromagnetics faculty. While some of them do enjoy the subject, but they don't guide the students towards a particular target. Okay, so my strong plea is to make a certain target for that and design the content of the course accordingly. Then comes another subject, which is called electronic packaging. Somehow, in any institute that we contacted, none of them are even familiar with the word electronic packaging. That means the students graduate from all the programs, including, I feel that including IITs, they graduate in electronics without knowing what electronic packaging is. Now, what is an electronic, let us say, equipment or package? You have today certain ICs, certain discrete components put together on some substrate. Substrate, that is what we call a printed circuit board, and the goal is to reduce the area of the printed circuit board, and also if the frequency of operation is very high, the lines interconnecting the devices also start becoming like antennas. So what happens is, and then each device, because the number of transistors in a device is continuously increasing, even though each transistor on the device consumes very small amount of power, but when you have almost 1 billion devices in one microprocessor, obviously the amount of heat generated will also increase. And you are required to remove the heat as much as possible to keep the electronic devices under operating conditions. If the temperature goes beyond 120, it ceases to be an electronic device at all. So the major issues is physical size of the board. How do you do interconnections? When the device is complex, the number of input-output pins can be very large. They can go up to few hundred. And how do you interconnect them? When you interconnect, obviously, any kind of graph that you draw, interconnecting them, the lines will crisscross. When the lines crisscross, obviously you cannot put on one surface. You require multiple layers. That is, you have to go under one layer and connect to the other one. Now, some of the high-end mainframe computers, the packaging requires something like even 20 to 30 layers of substrate. Whereas most of the other equipment requires boards with up to maybe 6 to 7 layer, 6 or 7 layer boards are required. So how do you design? You are required to design a multi-layer printed circuit board, and at high frequencies, because they start transmitting the signal to the next one through its field, you have to make sure that the signals do not get distorted. Not only that, when you send a pulse, even a small length of copper connection, the signal will get distorted by the time it reaches the other side. So you call it signal integrity. That means from the point of generating a pulse to the point of receiving, the pulse shape should not get distorted. And so you have to ensure signal integrity. So if you look at this, then you have issues like, as I said, multi-layer board. And when you put a high density package with large number of input output pins, you require special type of soldering onto the printed circuit board. So there is a lot of things that one needs to know when you want to design an electronic circuit. So electronic packaging course will sensitize at least the student to issues involved in designing an electronic circuit. If one wants to go towards the even IC design also will be the same thing. You have a substrate, and then you have individual devices which are interconnected at that device level. They may be very small in size, but the same issues will come, namely signal integrity, that will have to be attended to when you design the IC itself. So at least at the board level, if the student is trained, then he can transfer that knowledge to the IC design level as well. So we strongly suggest that the ECE curriculum include one course on electronic packaging. You don't become a specialist with this, but you know what are all the issues and what are the methods people use to take care of these issues. Okay. So this kind of analysis of the subjects involved in any curriculum should be done before you start designing the curriculum. So in the case of ECE, we felt that these are the standard courses that are at least the first 4 are being offered by or use textbooks which are very dated, and then students lose interest in that. Now we come to the curriculum proper. Curriculum structure we have presented in the earlier one. We follow the same thing: Humanities, Social Sciences and Management 19 credits, Basic Sciences 16, Engineering Sciences 14, Professional Core 50, Professional Electives 24, Project and Internship 16, Open Electives 9, Skill Enhancement Courses 12 credits. So This is what we present. Once again, as I mentioned, this is not unique. But 150 to 160 is mandated by NBA. So you cannot exceed 160. So you have to distribute among them. And then keeping the distribution should be kept in mind, should take into consideration, because 4 years after the students enter your program, they are coming to the market, and what kind of knowledge and skill set they require. And as the number of credits is limited, one cannot overload the curriculum. So the courses are, our credits are at premium. So you have to be extremely careful in either rejecting or accepting a course. Okay. Now, basic sciences, we said 16 credits. Here we talk about a first course should be, unfortunately, in the case of mathematics, people have been using some kind of engineering mathematics textbooks, which are good, no doubt, but they're actually collections of topics. In my opinion, the first thing the student should get exposed to, because all engineering systems, irrespective of the branch, are dynamic in nature. That means the variables concerned with them change with time. When you want to model any engineering phenomena, they have to be done at least to start with linear ordinary differential equations. Some of the IITs spend a lot of time in teaching a lot of calculus, which has been the what do you call practice for several decades, because it has come from USA. Unfortunately, in US universities, still they teach a lot of calculus as a first course, and they have issue in that. People don't perform well because of the nature of the students, and they have a lot of research being done. How do you ensure that all people pass? First of all, why design a curriculum that is irrelevant at that stage, and then work out a method? How do you teach that to the students? But the first thing that an engineering student know, what is the nature of dynamic system? We have done that in some universities. People have mathematics faculty have worked on it. In fact, they wrote even textbooks on that. So it is quite workable to have first course on linear differential equation, a 3:1:0, or it can also be 3:0:1, because a lot of software tools are available. If you have that, they can really understand the behavior of differential equations in a 3:0:1 course. Then another one, in today's context, everywhere data processing is important, and especially with AI, you handle large databases, and you should try to find out the patterns from that. So a first level of knowledge of statistics, not probability theory, first level of knowledge of statistics is absolutely necessary for all engineers. We suggest a 2:0:1. Using some software tool, you can at least introduce basic things about statistics in second mathematics course. Then the current practice is to use one course in physics and one course in chemistry. But again, because of the widening of the scope of programs, you are also considering biology as one option. So what I felt is, you can have a physics and chemistry, some topics put in together, what you consider important for ECE. Let's say 3:0:1. What is the chemistry for an ECE program? The best would be electrochemistry. Physics for the ECE students can be offered. Once again, the 12th standard physics is already quite high. In many places, you find the repetitions of 12th standard physics back in the engineering programs. So don't fall for that. Then we require partial differential equations. This is one suggestion. As I said again, the faculty together will have to decide, required for some of the communication courses. And then instead of a separate chemistry course, we suggest a biology for engineers, as many people are going into specialized electronics, like electromedical systems and so on. Okay, these are the 16 credits for basic sciences. Then engineering sciences, linear electrical networks. This is necessary, but here you have to be careful what do you want to teach. Don't make it too, too applied mathematics type of course. In fact, the most popular book on electrical circuits is the author himself says that it is applied mathematics course. So what is it that you need to learn in linear electrical circuits? You should know what are the signals that you work with, what is the behavior of basic three electrical elements that you have, that is resistor, capacitor, and inductor. When you put them in different combinations, how does it process the signal, and what is the output from that? That one needs to know. And that is one-port network. Apart from one-port network, people have to understand two-port networks as well, both active as well as passive networks. So, but we need to restrict, because it's the first course, to linear electrical networks. And forget about, there are two things that you talk about. Electrical circuits, they call it. In that, what they do is they not only teach network theory, but they will also talk about physical passive devices like resistor, inductor, how it is made, what kind of parameters does it have, and so on. But if you remove the practical devices, because practical devices have been changing also continuously. Now most of them are what you call as surface mount devices. So linear electrical networks is restricted to hypothetical components, pure resistor, pure capacitor, and pure inductor. And how do they behave under various signals and different combinations that you put the elements together. That can be done, and that course comes out quite well. One can really try that. Syllabus can correspondingly be designed. Please don't go by the available textbooks. Then you require to know today computational thinking. That course can be a course on C or some other language, but one should be able to think computationally. Once you understand, that means you have to convert something, an operation, into some kind of algorithm. That algorithm can be programmed into through some language and implemented on the computer. Okay, a computational thinking, and here they have to practice quite a bit. That's why we converted into 2:0:2. And then the control systems I've already mentioned. That will be engineering science course, 2:0:1. You restrict yourself predominantly to time domain methods, and all of that can be practiced in the lab on your laptop using Scilab or MATLAB. Then another theoretical course will be signal processing systems, 2:0:1. Okay, now come humanities and management. 19 credits we talk about. English, 1:0:1, which many of the colleges are already doing. And we propose these three courses. Again, you have choice here. Each department can slightly take a different set of courses. Energy and society for both electrical and ECE programs. It can be water and society for a civil engineering program, and so on. Sustainability is another one which is required to address PO7 and so on. And another course is development, where you can call it what you call service learning course. Okay. And then project and finance management. There are standard textbooks available for this. And once again, here also you can use lab to plan your project, and the Microsoft project can be used for that, or any other project management package. Professional communication, that is something that people have to be familiar with and should also master. 1:0:2, and then you have several topics put together: IPR, ethics, and constitution. This is also requirement from the NBA. Some familiarity with the constitution, so you can give 1 credit worth each in each one of these areas. Now, professional core, 50 credits we talked about. So you have engineering product design. Here, while it is engineering product design, it will be predominantly either communication or electronic product. Functional design of digital systems, that's what I mentioned already. Some instrumentation, because you constantly work with a variety of instruments, so one should be familiar with. It need not get into what you call a lot of theory about the transducers and so on. One can say which are the standard instruments that are used, and the theory of it, and what are the errors that you are likely to expect, what are its limitations, that can be taught, and they can practice something in the lab. Then you have analog circuits 1, 3:0:0, and you have analog circuits 2, 2:0:1. So the second course will have a full laboratory, which will use the material both from analog circuits 1 and 2. Then you have microprocessors and microcontrollers. If you want, you can change the name to simply microcontrollers as well. So you have 3:0:1. That's a 4-credit course, which goes with the laboratory as well. And then you have digital signal processing, which will be continuation of your first course in engineering science. And then you have analog and digital communication systems, computer networks, designing with FPGAs, system and network programming with embedded C, electromagnetics, wireless communication systems, PCB design, microelectronic systems packaging is the other course. So these are the 50 credits that go towards making an electronics and communication engineer. Now, open electives, you are talking of 9 credits. So I'm giving a long list of courses here, which you can either offer through the humanities and social sciences as well as in open electives. So I don't have to read the list. We have looked at these titles in the earlier unit. So you have a choice here depending on you can have some kind of advisory committee to select from here what kind of open electives your department should offer. You must have the resources also, right? And interest of the faculty as well. Then projects and internship, we propose 2 mini projects, each one 2 credits each. And final project 8 credits, and internship 4 credits. This is what many colleges follow. Then you have electives, electronics bouquet. Every bouquet has 24 credits. Again, the list here is not unique. You can change. So here I proposed one set: VLSI design and technology, analog IC design and layout, mixed signal systems and data converters, RF and microwave circuits, power supplies and battery management, power electronics and motor drives, sensors, MEMS and instrumentation, AI for hardware design and testing. So if a person does the 50 credits of core and 8 of these electives, then I think he can become a very good electronics engineer, covering a wide range of areas of application. Communication bouquet consists of advanced wireless systems, 5G, 6G, antenna design, RF system design and measurements, optical communication systems, information theory and channel coding, networked IoT systems and protocols, security and privacy in communication networks, machine learning for communications. And signal processing bouquet will consist of advanced digital signal processing, statistical signal processing and estimation, adaptive and array signal processing, image and video processing, audio and speech processing, biomedical signal processing and wearables, real-time DSP systems and FPGA implementation, deep learning for signals and time series. These are the courses. As I said again, this is not a unique bouquet. You can have different flowers in the bouquet. Okay. Now when we arrange these things, because of the requirement of multiple entry, multiple exit feature, we have to clearly define what are the employable skills at the end of the first year, second year, and third year. Because you get a certificate, you get a diploma, you just get a diploma after 2 years, and after that very few people leave after third year, but still if somebody leaves, he can get his certificate as well as this set of skills. So what is the employable skill? Some of these things are suggestions. Produce digital, audio and visual records. Can I produce information in digital form, both audio and visual? Manage data for business and education. Provide simulation and measurement support in the areas of electronics and communication systems. Provide support to designing and developing an engineering product. Write simple programs in C. Understand the complex relationship among people and energy and environment. So here, what happens, at least he goes out after the first year with a set of skills which are employable, which are usable by the industry. So here, this is how we are arranging the same set of courses that we have given. Generally, it is about 20 per semester. Sometimes it can become 19. Sometimes it may go up to 22 as well. Because last semester will have, 8th semester will have less number of credits. So you have linear ordinary differential equations, physics and chemistry for ECE, engineering product design, English, energy and society, and digital audio visual production and engineering. Then semester 2, statistics, functional design of digital systems, linear electrical networks, basics of programming using C, instrumentation, sustainability. Another skill development course is data management tools for business and education. And employable skills at the end of second year, design and simulate analog and digital circuits and systems, acquire AI skills professional engineers need, determine the performance of analog and digital communication systems, identify and formulate problems of development in the local context, design simple digital signal processing systems, design and simulate simple control systems using MATLAB or Scilab. Okay, these are the courses which are arranged for this. Semester 3, as you can see, 22 it goes up to. And biology for engineers is taught really in the 4th semester. And you have, this is a skill enhancement course, AI skills for professional engineers. Again, as I said, this was a choice I made, but from the list that we have provided, you can actually pick whatever the department feels. Here you can have a mini project, first mini project. And Employable skills at the end of third year: design embedded systems for electronic systems, architect and operate computer networks and wireless networks, communicate in written and oral form professionally. This is oral form professionally. Understand how to work as a responsible professional. Understand how a project is managed. So the courses are set here, and electives will start really at the semester 5. Okay. You have really 8 electives. We consider that all electives, for the convenience of planning and distribution, they're all made 3 credit courses. Okay. And at the end of 4th year, understand the role of packaging and design of electronic systems and ICs. Understand how a project is managed. Design and develop electronic communication products and systems, because that is a major project the students do. So here, if you look at, you can see most of the electives come here. Microelectronic systems packaging is the only course, core course, and open elective will come. One open elective will come here, and another open elective comes in the 8th semester. Elective 8, project phase 2, and internship. How do you manage all these in the 8th semester? Different colleges follow different methodologies. You can, depending on your geographical location, you can plan the way you find it convenient. But as you can see, we are within 19 and 20. Because of that 16 in the 8th semester, we went for 22 in 1 or 2 semesters. Okay, so this is one sample of ECE curriculum, and whatever sequence that I went through, you need to go through for your branch with all the department faculty for participating, but don't try to come to conclusion in one meeting. You spend considerable time, you can have online interactions, and people can present their views, and then you can put it together. And also my strong plea is, don't go by what you have been teaching or availability of textbooks. Today, content is not an issue. You can put together fantastic content from the internet. In the next week, we will try to understand the nature of instructional system design. Once we do that, we move on to what do you call course design. What is the process that you would like to follow in designing a course? And thank you very much for your attention.